Okay, so this is going to be, what we're going to see here is a really beautiful proof that there are arbitrarily large gaps in the prime numbers. A pretty surprising fact. One of the really beautiful things about number theory is that you can prove really surprising, really sort of far-reaching results just with simple kind of arithmetic. This is what we call an elementary proof of this pretty surprising fact. We've already proved, and if you haven't seen it, take a look at the video on that, that there are infinitely many prime numbers. We do that also with basic arithmetic. That's a proof that was known to the ancient Greeks. So this pretty surprising thing that there's infinitely many prime numbers. We proved that using basic arithmetic. Now we're going to prove, also just using basic arithmetic, and this is the really sort of pinnacle of math, the amazing beauty of math at work here, that even though there are infinitely many of them, you can get arbitrarily large gaps in the prime numbers. So that means if we have any n in the natural numbers, a positive integer n, we can get n consecutive composite numbers. And not only are we going to prove this, but this is going to be a constructive proof. This would be for all n in the natural numbers, by the way. This is going to be constructive proof. We're actually going to construct these n composite integers using just basic arithmetic. The fanciest thing we're going to use is the factorial. N factorial is defined to be n times n minus 1 times n minus 2 all the way through 3 times 2 times 1. So it's n times all of the numbers which are less than n down to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is, I think that's 120. And we're going to use this, we're just going to use these factorial thingies to construct n consecutive composite numbers. The first one is going to be n plus 1 factorial plus 2. That's our first one. We should get some different colors going on here. This is getting kind of boring. I already used that one. Maybe this is a nice color. N plus 1 factorial plus 2. That's going to be the first number. The second number is going to be n plus 1 factorial plus 2 plus 1. And then we're just going to keep adding. We're going to keep adding until we have n of these. When will we have n? And also I'm going to write the general term, as we call it. I'm going to write, oh, and my battery is low, but that's okay. We'll make it through the video. N plus 1. It's a nice, quick, simple, extremely elegant proof. And n plus 1 factorial plus 2 plus k. Here is the general term, plus k. And then all the way down, the last one is going to be n plus 1 factorial plus 2 plus n minus 1. And so this is n numbers, because the first one was n plus 1 factorial plus 2 plus 0. So we counted from 0 through 1 all the way through n minus 1. How many numbers are there from 0 to n minus 1? There will be n, right? From 1 to n minus 1, there are actually n minus 1. We started counting at 0, though. So these are the n numbers. And the claim, we're going to claim that they are all composite. They are all composite. How are we going to prove this? So we're going to go straight to the proof of the claim. And again, this is going to be remarkably sort of straightforward given how broad a result this is. Well, if n is in the natural numbers, right, then n is bigger than or equal to 1. So since n is bigger than or equal to 1, this means that n plus 1 factorial is even, right? Because n plus 1 is bigger than or equal to 2. 2 factorial is 2 times 1, which is 2. And then any of the higher factorials have a 2 somewhere in there, right? Like 5 factorial, you have 5 times 4 times 3 times 2 times 1. 2s are actually the most abundant primes in factorials. When you take a factorial, you're multiplying a bunch of numbers together. If you look at the prime factorization, and do check out, if you haven't seen stuff on prime factorizations, take a look at the video on fundamental theorem of arithmetic, sort of beginning of number theory, and the arithmetic functions of number theory, including the number of prime factors function, or the number of positive divisors function, which uses the prime factorization. But the point is that they're all going to be, except for 1 factorial. So 1 factorial is 1, 0 factorial is 1. That might be a bit surprising. Take a look at there's a video on that as well. It's defined to be 1, and it just basically doesn't cause any contradiction, so it's okay. But if a number is bigger than 1, a positive integer is bigger than 1, like n plus 1, then n plus 1, or n, if n is the number which is bigger than 1, that factorial is always even. So n plus 1 factorial is even. So this means that n plus 1 factorial plus 2 is even, so it's composite. Actually, not so it's composite. It's even and it's bigger than 2. 2 is prime. 2 is the oddest prime, as we say. It's a math joke. It's the only even prime, which makes it very odd in a different sense of the word, odd. So n plus 1 factorial plus 2 is even, so that one's composite. Then what about the other ones? And this is the way we always prove things about n, or one of the ways we prove things. We often prove things this way. If I want to prove that's true for all of these, for any k, 1 less than or equal to k less than or equal to n minus 1, so I want to prove it's true for the rest of them, for the general term, n plus 1 factorial plus 2 plus k, where k is in between 1 and n minus 1 inclusively, so including the possibility there could be 1 and n minus 1. Well, how am I going to prove? I'm going to prove that n plus 1 factorial plus 2 plus k is composite. So it's a product of two numbers which are smaller than it. How am I going to do that? Well, let's note that since 1 is less than or equal to k, which is less than or equal to n minus 1, if I add 2 to this, then we're going to get 3 is less than or equal to k plus 2, which is less than or equal to n plus 1. And so this is n plus 1, that's 3, that's k plus 2. So k plus 2 is in between, and this is of course the same thing as 2 plus k. This means that when we take, k plus 2 is less than n plus 1, so this means that when I do n plus 1 factorial, it's going to be n plus 1 times n minus 1, all the way down to k plus 2 somewhere, through 3 times 2 times 1. So this means that k plus 2 is a factor of n plus 1 factorial. We would say that k plus 2 divides n plus 1 factorial. This line, of course, means, and we use this a lot in number theory, this line means divides. K plus 2 divides n plus 1 factorial. What does that mean? That means that n plus 1 factorial is equal to k plus 2 times some integer m. We'll say m is a positive integer. Of course, here m is n plus 1 factorial divided by k plus 2. That will be an integer precisely because k plus 2 is a factor of n plus 1 factorial. So n plus 1 factorial is divisible by k plus 2, and that means that n plus 1 factorial plus 2 plus k, or plus k plus 2, which is the same thing, is also divisible by k plus 2. So n plus 1 factorial plus k plus 2, and I'm just rearranging the k plus 2, or the 2 plus k, to be a k plus 2. This is, just to write it out explicitly here, this is m times k plus 2 plus k plus 2, which is, we'll factor out the k plus 2, that's k plus 2 times m plus 1. So that's k plus 2, m plus 1. And I know that k plus 2 is bigger than 3, and it's less than or equal to n plus 1, which means that it's strictly less than n plus 1 factorial, n plus 1 factorial, and that's because n plus, so the only numbers which are equal to their factorials are 1 and 2, and so if k plus 2 is bigger than or equal to 3, and n plus 1 is bigger than or equal to k plus 2, then n plus 1 is bigger than or equal to 3, so it's less than its factorial. So k plus 2 is less than n plus 1 factorial, and therefore less than n plus 1 factorial plus k plus 2. And then the m plus 1 also is going to be, because m plus 1 is, as we've seen, m as we've seen, m is n plus 1 factorial over k plus 2. This is actually also going to be less than n plus 1 factorial plus k plus 2. Although as I'm writing this, I'm realizing we don't actually need to prove it. It's divisible by one number, so k plus 2, so 1 is less than k plus 2, which is less than n plus 1 factorial plus k plus 2. So this means that n plus 1 factorial plus k plus 2 has a proper divisor. So it's divisible by a number which is less than itself and bigger than 1. That means it's divisible by 2 of them. We don't actually need to show it. I was just going to go and start proving that this is less than n plus 1 factorial plus k plus 2 and bigger than 1. But we actually don't need to do that. And we'll keep this proof as nice and simple and elegant as we can, because this just proved that the general term, that each one of these, for every k in between 1 here and n minus 1, n plus 1 factorial plus 2 plus k is composite. And this might seem like a lot of stuff. You're looking at this thinking, well, this is a lot of things going on all over the place. But think we just proved about an infinite set of numbers, right? We proved that we have a video on that. Again, check that out if you haven't seen it. This really lovely proof that there are infinitely many primes, which is even simpler than this. And then just using some multiplication and factorials and things, we proved that no matter how big a gap you want to find in the prime numbers, you can always find a string of that many consecutive composite numbers. Although there are infinitely many primes, they get more and more spread out. They get very sparse as you go up. And this is a really remarkable result that we proved using very, very sort of limited mathematical machinery. And this is, I like to throw in this quote as often as I can in the number theory videos. So Gauss, the great mathematician, famously said that math is the queen of the sciences. And people quote that a lot. They often forget there's a second part to that, which is he said, and number theory is the queen of math. And the reason is just this amazing sort of simplicity and elegance and beauty to number theory, which is why I always suggest it as I probably should have mentioned this at the beginning of the video. I'll try to put it at the beginning of other videos, but I like to suggest number theory as a nice starting place for people who want to get interested in math. And I think, of course, that everyone should be interested in math. I think that people should get much more interested in math than they are. Generally, people sort of have a bad experience with it in high school or junior school. And it's really unfortunate because it's so nice, but it's often presented in a really unfun, sort of horrible way, and it's seen as drudgery and a chore. But it's really this amazingly beautiful thing. And you can, one of the great ways to start to see it with not that much background, even if you haven't done a gigantic amount of math, is getting into number theory. And this can sort of pique your interest, and you can see the beauty and the elegance. And I'm realizing how pretentious this is sounding. I'm going to stop the video, but hopefully you enjoyed this and are motivated to go and learn more stuff about number theory and math in general.